Good morning, Year 7s. Alright, today we are doing our third algebra lesson, and it is on multiplication within algebra, so multiplying different algebraic expressions together. And it uses something called the first index law. Now there are about, depending on how you classify them, 6, 7 or 8 index laws, and I think you tend to learn them all in grades 9 and 10. We're going to learn at least half of them in Year 7, because I think you guys are up to the task. But we're going to take it nice and slow, and today we're just looking at the first index law, whatever on earth that means for you guys. So today's learning intention, to multiply algebraic expressions using the first index law. Now this presentation and the exercise you're going to do after it, this is either a 1 hour lesson over Monday and Tuesday, or you can do it as 2 half-hour sessions each day to get the whole thing done. Okay, so let's dive straight in. So here is the first index law. All right, firstly, a couple of definitions. Now, these numbers here, well, they're variables at the moment, but they can be anything. Those are the bases, okay? And these here are the indices, which you would normally call the powers. We tend to call them indices. They're not power laws, they're index laws. In America, they call them exponents. But it doesn't really matter what word you use, okay? We have bases and indices, or powers, or exponents. And that's just a little bit of language. Now, if you have the same base, and those two bases have different powers, okay, and those bases raised to those different powers are multiplied together, then the answer is that base written once to the power of the two indices added together. So when we multiply bases, we add the powers, okay? Now, students find that confusing, okay? They see a multiplication sign here, and so they multiply typically the powers here and things like that, all right? So that's the sort of thing you need to avoid. But I'm going to go through why this actually works in the process of doing a bunch of different examples, and hopefully after that it'll make a whole lot of sense to you, okay? All right, so we're going to do literally like 14 examples because I'm trying to cover every little situation that you might encounter that will be difficult for you. And just as a reminder of what that law is, I've got it written up the top right hand corner of every problem that we do, okay? All right, so question 1, m squared times m cubed. And the instruction is to always simplify. All right. Now, if I were to write this in expanded form, I would write m times m, that's my m squared, times m cubed, which is m times m times m. And you know how to go from expanded form into index form. You write the base, you count how many times that base occurs, 1, 2, 3, 4, 5, and that becomes the new power. But if you think about it, this step here was entirely unnecessary, because how do you get a 5 from a 2 and a 3? Well, you add them together. 2 plus 3 equals 5. So all you need to do to get the power, if you have same bases multiplied together, to get the power of the answer is to add those two indices together, and you will have your answer. All right, so once again, let's, just in case that didn't make sense, let's do the exact same thing again. X to the power of 4 is x times x times x times x times x squared, which is x times x, which equals x to the power of something. Well, to the power of what? We count the number of x's. 1, 2, 3, 4, 5, 6. X to the power of 6. But this step here was unnecessary because 4 plus 2 equals 6. All right, so from now on, we can skip this step here. And that's what we're going to do now. Y to the power of 5 times y to the power of 7. I could write out a bunch of y's with multiplication signs in between them, but I'm not going to do that because I have this lovely first index law here. So I'm going to write y once. I'm going to add the two powers together, and I will get y to the power of 12. Nice and straightforward. Feel free to pause any time, guys, if I'm going too quickly, but also the full PowerPoint is available on Classroom under the Algebra tab, and it will have additional points and tips written inside the presentation, and it won't be my handwriting. I've typed it out properly. So you have that resource there to go through real slowly if you need to. Okay, so don't stress. Oh, what's going on here? We have a negative power. All right, let's take care of that. The thing is, with the index rules, a rule is a rule. Okay, so if we just follow the rule, even though something unfamiliar has popped up, a negative power, we're still going to get the right answer. So the rule says we write down the base once because the bases are the same, so our rule will work. And we add the powers. Well, 7 plus minus 5. Okay. Now, plus minus, we know from previous studies that a plus and a minus next to each other means a minus. So, q to the power of whatever 7 minus 5 is, which is q squared. Okay? And once again, if you can do this second step here in your head, that's absolutely fine to go from here to here. All right. Making nice progress. Oh, here's a tricky one. And you can see from what I'm doing here, guys, I'm trying to pull up examples of all of the typical little issues that stump students, okay? Here's a really good example. People see this index law and they go, all right, the bases are the same, so I'm going to have one base in my answer, P, and I have to add the powers on the left-hand side of the equation to get the new power for the answer. 7 plus 0, because there's nothing written there, is 7. But that is wrong because we know that mathematicians are lazy, and if you have P7 times P, that really means P7 times P to the power of 1. Okay, so if a variable actually and a number doesn't have a power, it really does have a power. There's just an imaginary 1 written there, and you just have to remember that. And if it helps you to remember that, you can actually draw it in like I've done just there. Now we can do 7 plus 1, which equals 8, P to the power of 8. All right, so that's another little issue covered. Okie dokie. Oh, what's going on here? The bases are different. Can we even answer the question? So the question is simplify u cubed times x squared. Well, the rule here says that the bases need to be the same. A and A. Well, here we have u and x. They are different. So can this question even be answered? It certainly cannot be answered. Cannot be simplified. And this is a huge point of confusion all the way up to year 12, if you can believe it, okay? People constantly try to simplify things in algebra that cannot be simplified, okay? U's and x's are different things, so we cannot combine them in this way. We cannot say u cubed times x squared equals, I don't know, u to the 5 or x to the 5 or ux to the 5. None of that makes any sense. U cubed times x squared simply equals u cubed times x squared. It's kind of like with collecting like terms. 2 apples plus 3 bananas, 2a plus 3b, doesn't equal 5 banapples, or 5 bananas, or 5 apples. It's just 2 apples and 3 bananas, or whatever I said, okay? So some things in algebra simply cannot be simplified, okay? That's really, really important to remember. So if the bases are different, you cannot simplify. And it also works with numbers, we can't forget. I mean, don't think of variables as too different from numbers. Variables are things that can be numbers. We just don't know what the right values are for the variables yet, okay? So all of the index laws that work for variables also work for numbers. So, do we have the same base? Yes, this wouldn't work if it was a 2 and then a 4 as our two bases. We have the same base, it's a 2. So we write down a 2 once and we add the powers. 3 plus 2 equals 5. Now, I think in the worksheet that you're going to do, when you do just number problems with indices, I think it says keep it in index form, which would mean keep your answer in this form. But I'm gonna do something a little different and take this one step further, because if that was a to the power of 5, there's no way you can calculate a to the power of 5. But 2 to the power of 5, that actually has an answer. That's 2 times 2 times 2 times 2 times 2, which is 32. So when it's numbers, you have the ability to actually take that one step further, okay? And if you think about another way that we could get to 32, well, 2 cubed is 8, 2 squared is 4, 8 times 4 also equals 32, okay? So it all comes full circle. All right, what the hell's going on here? Now all of a sudden we have coefficients, and I'm trying to use as much of the correct terminology as I can. I could have said numbers in front of letters, but instead I want to say coefficients in front of variable parts. These are the parts that have variables. These are the coefficients. All right. So when you have coefficients and variables, it's a very straightforward process. You treat it as two separate problems, a numerical problem and then an algebra problem. The numerical problem, the number problem, is to simply multiply the coefficients. Forget about the b's, all right? So 3 times 6 is 18. Now we've dealt with the numbers. Now I write down a b and then figure out its power. 3 plus 5 is 8. Done deal. All right, so another level of complexity here, guys, because now the coefficients have different signs. They're not always going to be positive. So now we're combining what we learned about multiplying and dividing positive and negative numbers together, okay? But that's all right. The coefficients are -5 and -4. So we're going to multiply those together first. Now a negative times a negative is a positive. And because it's a positive, I won't bother writing a plus sign, because if there's no plus sign, it automatically means plus. So we're dealing with a positive number, and 5 times 4 equals 20. Easy. All right, now we're going to deal with the pronumeral parts. So the base is x, and the powers are 4 and 3. So 4 plus 3 is 7. So the answer is 20 positive to the power x to the power of 7. And don't forget, guys, it's just a convention in algebra to always put your number right up against your variable part, but there's an imaginary multiplication sign in between. In fact, x to the 7, there's 6 imaginary multiplication signs because it's x times x times x times x times x times x times x. But that's very cumbersome, which sort of means over the top. So we write the power 7 instead of all of those multiplication signs. All right, so I'm starting to really mix things up here. Now I've got some positive and some negative coefficients and some positive and some negative powers. No problem. A rule is a rule. So we're just going to follow it religiously. The coefficients are 7 and minus 4. Multiply those together. It's a positive times a negative, which is a negative. 7 times 4 is 28. And now we have to deal with the x. So I'm going to write down an x, now figure out its power. Minus 4 plus 5. Well, imagine the number line. Imagine you've got a dot at minus 4, and then you do 5 hops to the right. 4 hops will get you back to 0, but we have to do 5 hops. So we do 1 more hop to the right, and we get back to 1. So our power is x to the power of 1. But, like I've said, mathematicians are lazy. So if ever anything is something to the power of 1, we don't bother writing it. And whoever reads that solution will automatically know that if there's an x there with no power written on it, that means, it doesn't mean x to the power of 0, it means x to the power of 1. Okay? All right, so really starting to mix things up here. I've got coefficients with positives and negatives, and now I have a couple of different variables going on. But not a problem, because a rule is a rule. We can just use that rule 2 times, once for each variable. So let's do this. The coefficients, my stylus is really starting to die. 4 times negative 4. Well, a positive times a negative is a negative. 4 times 4 is 16. And we have an r to the something, a p to the something, an r to the something, and a p to the something. So I'm just going to set myself up with an r and a p. And then I'm going to figure out their powers right now. So I deal with them separately, like 2 separate problems. R has 7 and 4 as the 2 powers. 7 plus 4 is 11. Now P has 2 and 5 as its 2 powers. 2 plus 5 is 7. All right. So most of these you can just do in one line of working out, which I know you guys love. All right. Woo! What's going on here? Okay, so now I'm starting to really combine everything together. And if you start to get just a little bit lost in these ones, that's okay, because these questions, quite frankly, are beyond your years. But I want to challenge you a little bit and see how far we can get with this. So this is sort of an ultimate example of just using index law 1. And now we have 3 things multiplied together. So I guess I should clarify that this rule here isn't just limited to 2 bases raised to different powers multiplied together. I could have another rule that says a to the m times a to the n times a to the, k equals a to the m plus n plus k. All right? Or if I had 4 a's multiplied together with 4 different powers, the answer would just be 1a with those 4 powers added together. Okay, so you get my drift. So here we have 3 things that we're dealing with, all right? Each one of those has a coefficient. So we don't change our rule, our process. First, we multiply the coefficients. We do it in 2 steps. Negative 15 times positive 3. Well, a negative times a positive is a negative. and 15, so negative, and 15 times 3 is 45. All right, now we have negative 45 times positive 2. Well, a negative times a positive is a negative. 45 times 2 is 90. So the coefficient is going to be negative 90. All right. Now I have x's, y's, and z's going on. There's a y, an x, and a z here. Here there's just a z and a y, and here there's a z and an x. Let me erase some of this to make some space. So we know that our answer is going to have an x, a y, and a z, and I'm following the algebraic convention that we learnt in our first lesson, which is to always put the pronumerals in alphabetical order. Okay, let me get rid of that. Excuse my rubbish video making skills here, guys. All right, now we just deal with each variable, each base separately. Okay, so x to the 3. This part here has no x, but we do have an x to the 5 here. 3 plus 5 is 8. Okay. Now we need to deal with the y's. Here's one y, here's another, and there's no y over here. Okay. Minus 2 plus 4. Well, if we think about our number line, when we have a dot at minus 2 and we take 4 steps to the right because it's plus 4, we end up with positive 2. So the power on y becomes positive 2. Done. Now finally z. Where are our z's at? Here's one. In this case, we have a z in every part of this bad boy. All right. This first z here looks like it has no power, but hopefully we remember by now that really means there's a power 1. So you might like to write it there just to remind you. All right, 1 plus 2 is 3. 3 plus another 3 is 6. So there's our answer. Pretty neat, eh? Minus 90, x to the power of 8, y to the power of 2, z to the power of 6. Okay, we're almost there, guys. All right, now we have two problems with slightly unique things going on, and I want you to super focus. It's not hard, but there are a couple of new bits of information now that I haven't taught you before, and they're going to pop up in these two questions, and I want to see if you can remember it, okay? So here we go. Now, this looks like a simple problem, and it is, but there's just a little trick to it. Now, okay, so let's follow our process. 7 times 6 is 42. And we have a t squared and a t to the power of minus 2. All right, so I'm going to write down my t. And the power, well, I've got a 2 and a minus 2 that have to be added together. 2 plus minus 2, well, plus minus written together actually means minus. And what is 2 minus 2? Well, that's 0. Say what? T to the power of 0? What on earth does that mean? Well, let me let you in on a little secret. I'm going to change the color into the secret color, orange. Here is the new rule. And this is actually called the third index rule. It's a whole rule. Remember, we're doing the first index rule today, but sometimes a third index rule just pops up, and it's really easy to teach. Once you remember it, you've got it forever. All right, t to the power of 0. Well, what does that equal? Well, let me tell you the general rule. Anything to the power of 0 equals 1. Anything whatsoever. I could have some enormous thing in brackets. 2x plus 15 w plus granny plus your pet dog. If it's all in brackets, making it one thing, and there's a 0 outside, that whole thing equals 1. Anything to the power of 0 equals 1, okay? But there are a couple of things to be careful of. For example, 5a to the 0. Everyone says that equals 1, but think about it. A to the 0 equals 1. 5a to the 0 means 5 times whatever a to the 0 is. So that would mean 5 times 1, which is 5, not 1, okay? So, using that logic, going back to my favorite purple, 42 times t to the 0. Well, anything to the 0 equals 1. So t to the 0 equals 1. So we have 42 times t to the 0, which means 42 times 1, which is 42. So we had a question that had variables in it, and our answer is just a number, an integer, 42. Pretty cool, eh? So let's not forget this. The third index law, and that's written out properly, typed out real nice in the notes that go with this PowerPoint. So if after all these examples you want to go back over them, they'll be all nicely typed out without my terrible handwriting in a PowerPoint presentation in the Algebra tab on Google Classroom. All right, now one more question that I really want you to pay attention to, all right, because something weird happens here as well. Okay, so let's follow our process. Why am I working in the wrong color? Excuse me. All right. 3 times 2 is 6. Now I have an x and a y here, some x and y action over here. So I'm going to set myself up with an x and a y, then figure out their powers. 3 for the x and minus 5. So 3 plus minus 5. Now you should start being able to do this in your head. Plus minus means minus. So 3 minus 5 brings you into the negatives, doesn't it? So minus 2 for the x. Y to the power of 1. And this y over here to the power of 2. 1 plus 2 is 3. Now this is the first time you have had an answer out of all of these examples where one of the powers is negative in the answer. Now, some worksheets will let you just leave the answer like that, okay? But what that really means is the following. 6y cubed over x to the positive 2. So, if you have a negative power in your answer, think of that negative sign as a train ticket for that base to go downstairs. And when it goes downstairs, its power changes from a negative to a positive. Now, let me just make something up over here. The same thing applies if you have something like, I don't know, 2a over b to the minus 4. 3b to the minus 4. Now, the negative power here is a train ticket for that b part to go upstairs, okay? So the answer to that would be 2a b to the positive 4. You have to change the negative to a positive when it goes from bottom to top or from top to bottom, over the 3. The 3 still remains on the bottom because the 3 has a positive power, 1. This part, I suspect, has really confused you, and that's totally normal. I'm really pushing it with this one. If no one understood that, it really wouldn't affect your worksheet, okay? I'm just putting it in there for extra information. Now, this is actually called the fourth index law. The fourth index law says a to the minus m equals 1 over a to the positive m. But there's another way of writing it. 1 over a to the minus m equals a to the positive m over 1. But that last over 1 is unnecessary. So that's called the fourth index law. Once again, don't worry about that one if you don't get it. It's just index law 1 that I really want you to focus on, okay? All right, that was your entire lesson for today, which means you can stop right now if you like, or you can keep going for half an hour and do your worksheet. Otherwise, you can just do the worksheet tomorrow, split it into 2 days. What I would say, guys, is questions 6 and 7 are really hard, and I don't want you wasting hours and hours, unless you're into it and you've got the time and it's not stressing you out, trying to do questions 6 and 7. Do as much of it as you can within the time that you have, but your priority are questions 1 to 5. But, you know, if you get up to 6 and 7 and you got time, you're feeling up for it, have a crack, all right? But the main questions are questions 1 to 5, all right? And this is all explained in the home learning schedule. Sweet! Thanks, guys. I'm going to go and make our second video now. So I will catch you on the other side. Bye-bye.